Hello. So welcome to this last talk of the conference and of this session. So I would like to talk about a work with this topic on leveraging crowdsourcing techniques for schema matching networks, which is a work I did with Nguyen and Thanh. Hung was a PhD student of mine, and Thanh at the moment when we wrote he was a master student at EPFL. So I start with a general introduction on schema matching. So schema matching in the first place is it is a technique and a research field which aims to analyze the methods for establishing connections between attributes of independently developed database schemas. So actually, in this talk, I mainly focus on schema matching, but the results are very, very much linked to the ontology matching. I will return to this question very soon. So. It was a very active research field, especially in the 1980s, 1990s, and it continues to be very important, and there are even important new results in the recent years. So you can find two interesting surveys of the research in these two papers. There are a lot of applications of schema matching. In particular, it's very important in a company, so where you have several databases, and people are facing the situation. They want to integrate this data in different databases, and which are which use different schemas. So you need to establish some connection between the schemas. So a lot of work is done on developing tools which would help practitioners to realize this task. So in particular from the 90s, where people realized that this is an important task, people developed a lot of automatic tools, and in a way, a lot of, if you look the papers in the literature, a lot of work goes in the direction of you take some data set which includes some schemas, and you try to improve, and there is a lot of improvement in terms of quality. So one of the, for example, the talk that we have seen before is also in this direction, which analyzes better and better functions to evaluate the similarity, which in some cases improve the matching quality. I mean, we have seen now the improvement in the similarity measures, but there are also a lot of techniques to improve based on on the structure and other attributes of the schema, other properties of the schema. So, nevertheless, there are. So, if you look this situation, there are a basic problem with this approach, because there is a blind hope that we improve, and we will have a better and better system. So, actually. If you look the type of methods which are used, they are often very heuristic. They do a lot of heuristic similarity measures, a lot of reasoning, which might be true in some cases but not in others. So the reality is that these automatic schema matchers they help in the practice, but they fail to produce correct results. So, which is not a surprise, because they are heuristic techniques. So they fulfill their role of improving this experience. So, like a practitioner has a lot of benefits from these tools, because he doesn't need to start from the scratch. He has a good start with the help of these tools, but they never arrive to produce a completely correct set of correspondences. So very often there is a need for a post-matching phase. So basically you have the output of the schema matchers, and you need to verify them, adjust them, maybe you add some or delete some. So there is this post-matching phase. And actually, if you look at the situation in companies, this is the most costly phase because the company invests in the schema matching tool, so this is a one-time investment, but after that, the cost of the company is really the expert who is sitting there and working and thinking about how to resolve the problem. So actually this post-matching phase is really, really important. It's not, this is the real cost of schema matching in the praxis, and so in our work, we try to address this phase. Actually, there is an excellent work by the group of the previous speaker from Montpellier who proposed one measure for like in a schema matching and ontology matching evaluation. Often the people evaluate on precision and recall, but actually they propose to use also some post-matching effort. So we will not exactly follow their metric, but actually we will study the same phase. So if we have the schema matching, they stop, and then we study the costly effort which is coming after that. So in our setting, which is a common setting in reality, companies do not have two databases on two schemas, but often they have a number of databases, and they are interconnected. So, and we will actually exploit this interconnectedness of the schemas. So, actually, the motivation for our research coming from the SAP, from the company SAP, who have a schema matcher in their software, and you can imagine that companies are installing SAP systems in different sites. So imagine a company who has different sites for sales. So one for Western Europe, one for Eastern Europe, one for Northern Europe, and then each of them has data about sales locally, and sometimes they need to exchange data. And they establish connections on a pairwise manner. Actually, this is another assumption that we make, that in our network, we assume that the schema matching is necessary, and we don't assume a central mediated schema, but we assume that the schema matching is pairwise. So actually, again, you can argue that in some cases designing a mediated schema would be advantageous, but in reality companies often have the problem that they have to match schemas pairwise, and this situation that we analyze this arises in practice. So this is a very special situation, very special setting, but this is not unrealistic, I would like to argue. So, and now I would like to share an observation. So even if we take the state-of-the-art schema matching tools and we apply pairwise schema matchings, the results are often very, very contradictory, because obviously the schema matcher doesn't take into account the network, so doesn't know what is the network. So, but companies and other settings where we have a network of schemas, they want to have some constraints on the network. So one natural constraint is what I explain in the next slide. It's maybe more clear that let's assume we have 3 schemas and we want to do pairwise matching. And let us look at the case of production date, release date, and screening date. So if we have the correspondence C4, C1, and C3, this is a very strange situation, because imagine you exchange data, and this part, I mean, this site, this database will have the same data in a different column. So actually people want to avoid this circles. So we don't want to have cases where you have a circle which is not closed. Circle means that we have a circle in the interaction. So these three schemas are meshed in a pairwise manner, and the correspondences what are proposed or which arise, they form a circle which is not closed. So we call this network level constraints, and actually in this work we assume two constraints of this type. I mean, this one is what we call a circle constraint, and the other one, which is, you can say it's a network level constraint, but actually the one-to-one constraint. So maybe you want to have a one-to-one correspondences between two schemas. So this is also a network level constraint, but a very specific one which involves two nodes only. I mean, but this circle constraint is a constraint which is which concerns the entire network, because it might concern several nodes. So so maybe I stop here for a moment for like having a more general consideration. So, by the way, this example is coming from a real data set. So we have obtained from, this is not from SAP, but from a British, so from an association from Northern Ireland, and they have three schemas of three companies, one of them BBC, and these schemas are about videos. So actually this and also the previous example is coming from a real example. So the general consideration what I would like to make, so what is an ontology? So because in the if you look the classical example what people cite in their papers is a shared formal conceptualization of the domain. But actually, if you look how ontologies are considered today, they are really formal conceptualizations of a domain, but they are not shared. So actually, here you can observe a situation where we analyze like this set of constraints about the network. This gives us like a shared assumption. So actually here we could consider, so this you can take it as a side comment, which I think is a very interesting one, that you can consider this set of constraints as a general set of ontology, if you want. But so take this as a side comment. So I would like to continue. So we have analyzed these schema matching networks and the phase of post-matching. So what happens that you establish this network, we assume we have this network, and we establish the pairwise connections, and we are facing the situation that there are a lot of problems. And there are even more problems than in the pairwise case, because this network level constraints you want to also satisfy. So you want to have a set of correspondences which all satisfy the circle constraints. So here is a short overview of the thesis of Hung. So this paper, what I present here on crowdsourcing, is I will go on present you the techniques we developed for this in this paper. So where we analyze crowdsourcing techniques to attack this problem. So how I will detail, but essentially, so we are facing a complicated problem, and we can ask a group of users to help us. And this is a common technique nowadays, or often used technique nowadays to attack problems which are costly and involve human interaction. Another paper which gives a more precise formal definition of the schema matching network, and presents several reasoning techniques which enable for a single expert who, like let's say the administrator of the company, to reduce his efforts, because as I said, here we need to take, when we fix the errors which arise in the pairwise matchings, we need to take into account the network constraints, and this makes the problem more challenging for him. So this work presents techniques which use reasoning to minimize his effort. The next paper on QPIS, QPIS 2003, presents other techniques where multiple experts can discuss and interact to attack this problem. So and in particular, we analyze a situation where you have experts who have contradicting views. Because it might also arise that some people might say, okay, this should be okay, this should be not okay. Because this correspondence is, also it is visible from the set of constraints. They are essentially, the correctness is determined by the context. So this is very well possible that even the experts disagree. And finally, we have in ICDE 2014, we have pay-as-you-go techniques which use probabilistic reasoning to obtain the most probable set of correspondences if you have only a very partial input from the user. So, but let us. This is the overall picture of the thesis of my student. So let's come back now and look the first paper I mentioned on crowdsourcing. So our contribution in this paper is to that. Okay, first of all, we define this model. We analyze this model. Then we design questions. So we use techniques to construct questions that we can pose to the workers in a crowdsourcing platform. Then we analyze how to handle the errors which are coming from because people might have erroneous input. And finally, we analyze how these constraints which we discussed, how they can minimize the cost again. In the setting of crowdsourcing. So let us have a look of the general architecture of the of our framework. So here you see a list of correspondences which are proposed by a schema matcher. From that we obtain with a module, we generate some questions which we pose via crowdsourcing platform to the crowd workers who registered there and answer the questions. Normally, in order to avoid errors, so or cope with the disagreement between the people, or and cope with the quality, we ask the same question several times in order to. I will speak about that, but essentially for the same correspondence, we will ask normally several questions from several. We will ask several people to analyze the same correspondence. After that, we will analyze, we will aggregate the answer, and as a next step, if we find that we will aggregate the answer, and if we find that the estimated quality is good enough, then we save in our database, or otherwise we will ask more and more. Otherwise, we will come back and we will generate more questions and ask and pose more questions. So in the following, I will speak about how to generate questions, how to aggregate, and also see how can we improve the whole process. So For the question design, we have essentially some schemas of schemes of some types of questions which we pose. So one of them is where we present a pair of schemas with some possible alternatives, and which are also generated by the matcher. And we ask whether, okay, we propose, okay, maybe in this case we have a birth name, and we have three alternatives, and we propose, okay, birth name. This is this what we want? Is this a correct matching? So, and then the worker can answer. So, in this same fashion, we also generate questions where we have not two schemas, but three schemas or more schemas, where we present together the schema, the matching results, and then the users can say which one of them is correct. So, for example, here you see 1, 2, 3, and he can say 1 and 3, these are correct. Or maybe he can say all of the 3 are correct, because this circle seems to be correct. In this case, here, again, he can say, here in particular it's important because we have here this problem with the circle, so he can also say, in this case, the 2 might be not correct, so that would mean that we ignore this, and this would resolve this problem with the constraint. So actually we did a very small scale user study with a group of students, so maybe it's not the strongest part of the paper, but actually presenting some contextual information additionally to the correspondence. This improves slightly the quality of answers. So, I mean, maybe it's a hypothesis which we tried to support with a small scale experiment, but this would really need a larger study. So, but I will move on to the more interesting parts of the paper, which concern the quality, the management of the quality problems. So, in this setting, so if it's a very common problem for each crowdsourcing platform that the user input has problems. So it might have many reasons why the input is incorrect. So this might be simply that the user just accidentally makes an error. It might be the case that user doesn't know it. He has a difficulty with the response because, as I mentioned, even the experts might disagree on some in some cases. He might have a lack of knowledge. Okay, so but we need to also cope with the case of malicious users, or with users who just give a random response in order to get the money. So. I forgot to mention that, but maybe you know this, the crowdsourcing platforms normally propose such micro tasks in return for a small amount of money. So it's observed that in many, these platforms have a lot of users who just register and then try to give random answers in order to obtain this, even this small amount of money. So we need to cope with this problem and take into account this noise which is always present in the input. So we are looking for techniques which might minimize the consequences of these errors which might come. So for this reason, we have chosen the so-called expectation maximization technique from statistic. Like the most basic aggregation methods would be to to ask the same question from a small number of users, for example 5, and take a majority voting. The majority voting has the problem that he doesn't take into account the if a user is accidentally or deliberately making errors. So the expectation maximization method develops for like obtains some quality metrics for each user. So we will be able to use this quality estimation of the responses which we obtained in the aggregation. So in other terms, with the help of expectation maximization method, we will ask the same question several times, and at the same time we are building up a database of user quality, user quality estimation based on the responses. So how it works, this essentially we assume some initial quality for each user, then we try to aggregate the answers. This gives us some aggregated results, and we can compare the aggregated results with the individual inputs, and this gives us an idea how well a particular user has responded. And then we might update and repeat this procedure several times. So essentially, once we have a set of probabilities about the reliability of users, these are or estimations about the reliability of users, and a set of estimations about the a set of answers, we can aggregate with our probabilistic model, which is again the expectation maximization. So, for example, if we have if we think that that based on our estimation of the reliability, the probability that the given correspondence is true is bigger than 0.5, then when we say is yes, otherwise we say no. Okay, so in any case, based on the user input, we obtain two numbers: the reliability of the particular user and an aggregated aggregated value for each correspondence. So now, if we, in this case, we did not work with real users, but we did a simulation. And in this simulation, to simulate a larger community of users. So in this simulation, we observed the natural phenomenon which anyone would expect. So if we ask more and more questions, then the estimated error rate gets lower and lower. So if we ask more questions, we get a better quality. So now we are facing again the situation where you want to minimize your cost, because if you ask more questions, we improve the quality, but at the same time it costs us more. The cost is very physical, so we need to pay the workers of the platform. So our goal actually is to push this curve down, so to develop techniques which enable us to reduce the actual cost, and with a lower number. The goal is that with a lower number of questions, we should get the same quality or a better quality. So this is our goal, and here we. Actually, our solution to this, or proposal to this problem is to use the constraints which we have in the network. So first, have a look what can we do with the one-to-one constraints in the network. So if we have one-to-one constraints, then show that we can exploit these constraints because, let's say, in this case, A B1 and A B2, like if you have these two alternatives as possible, and well, based on the one-to-one constraints, only one of them can be correct, then we can analyze the probabilities, and the case where true is appearing, we exclude this, and if we exclude, we can update the probabilities, and once we have updated the probabilities, we can show that actually we are, with the help of the constraints, the same, we can reduce the error rate in the present, if we assume the equal number of responses. So having this table enables us to lower the error rate. So in other words, we arrive the same estimated quality with a lower number of questions. So in a similar way, we analyzed the circle constraint and see how can we exploit this to reduce the error probabilities. And in the same way, if we look these three correspondences, then some of the combinations are not possible because it's not actually. Okay, some of the correspondences are not possible, which, I mean, here we need to take into account what is the probability what is the probability that this circle, that the errors, such circle exists that there are compensating errors along the circle. So for example, there are the errors compensating each other along the circle. So we first try to estimate this probability, and then with the help of this information, we can reduce the error rate in the aggregation, the estimated error rate in the aggregation. So in other words, because the estimated error rate is the number which determines how many questions we ask from people. So if we reduce this number, then we normally ask a smaller number of questions for the same correspondence. Indeed we have so we analyzed this with the probabilities, and also we did a simulation, and which confirms this, at least in the simulation. So we observed this behavior. So without constraints, this is the red, and with constraints, this is the blue, and this curve is pushed down. Okay, so I would like to conclude the talk here. So we analyzed the schema matching problem, in particular in a network. So we are looking at the problem of the schema matching in a network environment. We assume pairwise matchings, and we assume some natural constraints in the network. We introduced this schema matching network model, and our focus was the post-matching phase. So we would like to minimize the costs of correcting the errors, because this is the real cost in the company. So for this reason, we apply crowdsourcing techniques. The crowdsourcing techniques, we have presented how to construct questions based on a set of correspondences. We have analyzed how to aggregate the results such that we take into account the quality, and finally we analyze how can we further reduce the cost by exploiting the constraints which exist in the network. So thank you very much, and I'm happy to answer your questions.
Question?
In the data exchange problem, I know there is also schema mappings, and they have a constraint on the mappings that's called that they should form a weakly acyclic graph. And I want to know if there is a relationship between this constraint and your circle constraint.
Okay, so the data exchange problem is a very particular problem which people have studied in the database theory community, and actually there is a very little connection. So first of all, I should explain what is a data exchange, because I'm not sure everyone knows. So in a data exchange, you have two databases, and you want to put the data in one database to the other one, such that after that you can answer the same questions from the second database. And in particular, you want to have the same tuples, the same relations. So this work remains on the schema matching level. So actually, we assume very little about the schemas. So the schema exchange has a very, in the schema exchange problem, the tuples which are behind the schemas play a very important role. And actually, this weak acyclicity is based on the there are some FDDs and TGDs, tuple generating dependencies. So this weak acyclicity is defined for this special type of dependencies. So, and the dependency is for example, functional dependency is a special case of tuple generating dependency. So, obviously, functional dependency is a relation on the tuples. So we don't touch the tuples, actually. We remain on the level of schemas, and for us, the correspondence is just to say, okay, this attribute in this schema has a relation with the attribute in the other schema. So in our work, there is a second step. So let's assume we determine, okay, this attribute has a relation to another schema. You would ask after that, what is the relation? So maybe you have inter-schema inclusion dependency or some other dependency, or maybe just this is the same, but you need to do not a logical transformation, but let's say you have a transformation in one database you have the same number in euros, in the other in dollars, so you want to somehow. So there is a mapping expression. So for us, so we just try to find the connection, and the mapping expression is above this layer. So.
Another question? Other questions? I have a little question.
Okay.
In general, when we try to maintain constraints, we aim at minimizing the change we made on the data in order to satisfy these constraints. So there is a notion of minimal change.
Okay.
In your case, it seems to me that you have also this notion. You want to satisfy the constraints. Let's say, for example, you have these kind of cycles. It is a kind of transitive closure. The matching must define an equivalence relation.
Yeah. So
either you force to add a matching, or you remove other matchings. You say that A matches B, B is C, so A and C match. So either you add or you remove.
Yeah.
Do you have some?
Yeah. So actually, this is a very interesting question or comment. So when we started this work, so we also looked actually. So again, we are looking schema matching, but you are right that, for example, in data, there is one of the talks gave us related work or future work, the database repair. So, for example, if you have functional dependencies in a database, and then there is some violation, and then you want to do a you want to obtain the correct set with a minimal change. So actually, this minimal, so in a way, the minimality, how to say, we tried at the beginning of the project, we tried to construct, so one of the first, so as you have seen, there's a long project, and at the beginning of the project, this was one of the approaches. So what we tried that, okay, let's assume we have output from the schema matchers, and then let's assume that the schema matchers are mainly correct. So we would like to have, we started to look also heuristic techniques, as this is as the classical approach, okay? And one of our heuristic was to let's assume the schema matchers they report very good values. So maybe there are some errors, and then we would like to do a minimal change. But actually, this approach didn't work out very well. So and actually. Maybe we can discuss offline because I have a longer answer. Okay. But so essentially here we have a very different situation than the motivation for this minimal answer is really that you want to minimize the minimal repair is that you want to have minimal changes on your database. But here the goal is to have a better and better quality. So it's a very different motivation, and so might be a good heuristic in some cases, but for us it didn't work out well.
Okay, thank you. Another question? J'aimerais profiter de ma position ici, en tenant le micro, pour déjà remercier les exposants de la dernière session, et remercier aussi les organisateurs pour leur accueil formidable. On s'est senti très bien accueillis. Donc je me permets de parler au nom des présents. Voilà. Je remercie le speaker aussi. Et puis,